Okay, so I went over the fundamental theorem of the first fundamental theorem of calculus in class, and that was that the integral from a to b of f of t dt is equal to big F of b minus big F of a, where big F is the antiderivative of f of t. So if we're going to do something called a definite integral, we can just take the antiderivative and then evaluate it b minus a. So the first example I want to give you is, let's say we have the integral from 0 to 2 of the function 4 minus x squared dx. Now this is really the area from 0 to 2 of this function. So if I graphed this function, I would be looking at the area, something that looks like this. 0 to 2. But with the first fundamental theorem of calculus, I can just take the antiderivative and plug in the values. So that's what we're going to do. So we're going to take the antiderivative, 4x minus x cubed over 3 using the power rule. Then we're going to evaluate that from 0 to 2, and usually we're going to mark that with a little line, 0 to 2. And I'm going to evaluate that by putting 2 in here. So f of 2 minus f of 0. So I'm going to plug in 2 in for x and minus plug in 0. So plugging in 2, we're going to get 8 and minus 8 thirds. Minus, we plug in 0 and we're going to get 4 times 0, which is 0. 0 cubed over 3, which is 0. So we're going to have 24 minus 8, 16 thirds. And I didn't really ask for the area, so we're not going to put any units on this. We're just going to leave it as 16 thirds. Okay? All right, so the second example, similar. All there is to it is, like I said, you're going to take the antiderivative and then you're going to plug in values. So let's take a look at maybe -1 to 3 x plus 2 dx. This is another simple one. So all we're going to do is take the antiderivative using the power rule, x squared over 2 plus 2x, and we're going to evaluate that from -1 to 3. Notice here that I didn't put plus c. I don't really need a plus c because I'm evaluating the area, and it's not really going to make a difference with the plus c. So we don't really need the plus c when we do a definite integral. That's why when we did plus c, those were called indefinite integrals. When we have limits of evaluation, these are called definite integrals. So we're going to evaluate this from -3 to 1 by plugging in 3. And we're going to get 3 squared over 2 plus 6 minus, and we're going to plug in our -1. So we're going to get 1/2 minus 2. Remember to put this in parentheses just because you're going to have to distribute that negative. So we're going to get 9/2 plus 6 minus 1/2 plus 2. And we simplify this out and we get 12. So the next two problems are going to be from the homework. I'm going to do number 6 and 8. So if you want, you can pause this video right now, try your homework, and then I'm going to give you the even solutions here. So number 6 from the homework is the integral from 2 to 7, 3 dv. So we're going to take the antiderivative, which is 3v, and evaluate that from 2 to 7. So we get 21 minus 6, and that is 15, piece of cake. The next one on the homework was number 8, and that was the integral from 2 to 3 of -3v plus 4 dv. So again, we just take the antiderivative. We're going to have 3v squared over 2 plus 4v evaluated from 2 to 3. So we're going to plug in 3 in here for v, and then we're going to plug in 2 and subtract those. So we're going to have negative, so v squared is 9, negative 27 over 2 plus 12 minus, plug 2 in here, we're going to get 4, which is going to give us 12 halves, negative 12 halves, plus 8. Don't forget to distribute your negative in there, although you can just take this as 6 and then subtract will be 2. Do all the simplifying, and I believe you're going to get negative 7 halves. All right, so that's pretty much it as it goes to definite integrals. On Monday, we're going to just do a lot of practice. We're going to do a lot of antiderivatives, a lot of definite integrals, and maybe we'll get to see. You could possibly even check in your calculator if your answers are correct. Okay.